was there, his kids were doing an experiment. They were using food coloring and water to test diffusion. 1 glass of cold water, 1 glass of room temperature water, 1 glass of hot water. And you guys know what happens. They drop the food coloring in the cold water, and what happens? It drops straight to the bottom, it never spreads. They drop the food coloring in the room temperature water, and what happens? Spreads. Then they drop the food coloring in the hot water and spreads instantly, rapidly, right? And through that, it allowed him to reteach diffusion, but also taught them about heat as a kind of energy. Because this glass of water was hot, the water had more energy, so the particles of water were moving around more, and that's what pushed the food coloring particles around more. And I said, great job, you did a good job there. Let's talk about what the next step is. I think a cool next step, I'm not telling you what to do, Mr. Remy, but I just think the next cool step is tomorrow, or as homework tonight, let the kids design their own experiment. You tell them, hey guys, this is how I would do it in my class. Hey guys, good job today on the lab with the food coloring and the water. Everybody understands energy and diffusion a little bit better, but listen, I designed that experiment. Your turn now is a chance to think like a scientist and design your own experiment. So for homework tonight, I want you to design an experiment. You don't ever have to do the experiment. I just want you to design one. And I'm only telling you, your experiment has to have an independent variable, a dependent variable, a control group, and a set of steps. Bring that back to me tomorrow and let me see that you know how to design an experiment. Some of the kids actually do the experiment. Most of the kids don't, but they turn it in and I'm able to say, okay, I see you know how to design an experiment. Good job. But a few years ago, I wouldn't have done that. I would have let the kids do the lab that I designed, and then we'd move on to the next topic. I got to give them the chance to design their own experiment. Show me you know how to design an experiment. And if you don't, let me teach you how to design an experiment. When you design an experiment, the first thing you want to see is what are the 2 things I'm trying to test? Right? Heat and diffusion. Which one am I keeping the same? Which one am I changing and which one am I recording? I'm going to change the amount of heat and I'm going to record the rate of diffusion. Well, that's called a this and that's called a that. You know what I mean? Yes or no? Not, yeah? And then the very last thing is well, not the last thing. This is what I was talking about a minute ago. We've been doing a really good job of teaching kids the core ideas. The core ideas never changed. Lysosomes still do today what they did when I was in middle school. The core ideas haven't changed. But schools are forcing us now to teach kids science and engineering practice. And let me tell you where this came from. College professors have been saying this for about 20 years. Kids come to us and they know all the information, but when I ask them to figure something out, they're like, I don't know. Every kid that comes from Dalton High to Georgia Tech, they all know the equation for potential energy and the equation for kinetic energy. But then when I ask a kid to predict what happens to the amount of kinetic energy if we raise the velocity of an object, kids are like, I don't know. You see what I'm saying? So that's where this came from. So college professors passed this down to us and said, we need you to teach these kids how to think like scientists too. And what do scientists do? They ask questions, and they plan experiments, and they develop models. The model can be a picture, or it can be something you built, or it can be a cartoon that you created. You know what I mean? Assess frequently. But I talked about that in my keynote, didn't I? Good. Let me talk about that again. This was another one of those sample questions the DOE passed to me. And then the last one is, infuse rigor into your classroom. And I don't necessarily mean, cool. I don't necessarily, when I talked about this with my middle school, the last middle school I was at, I had to clear this up. I don't mean make the work in your class harder. A lot of people think, when I say I need to make my work rigorous, I need to make the work harder. I'm not saying that's wrong, but I'm also not saying that's right. You can make the work harder without making it rigorous. Rigor is about what you're asking kids to be able to do. You know? But understand that when I'm asking kids to do something more difficult, I have to, as the teacher, be comfortable with the difficult moment. A moment ago when I was starting this, when I had that thing on the screen with the explosion, I was asking y'all to ask questions. It was a little tense for a second because the room was really quiet. There wasn't anybody answering first until somebody answered first, right? And then it got quiet again and somebody else answered. But if my class is going to be rigorous, I got to be okay with the uncomfortable silence. Guys, I know I'm asking you to do something you've never done before, but I think if you think about it, you can do it. So I'm willing to wait. Who has an idea about why? I was going to do it with you guys. I planned to do it, but we're out of time. I was right here. I was going to say, let's practice asking questions right now. Let's look at a bouncing ball. Let's do it. Yeah, let's use our last 3 minutes that way. Imagine you guys were my class and I was the teacher. Let's ask some scientific questions about a bouncing ball that will deepen our understanding of energy transformation. And I'm standing in front of my room. Imagine me with a golf ball in my hand. I keep doing this. And I'm waiting on somebody to ask questions. Go. What's a good scientific question?
Could we graph the potential and kinetic energy?
Very good. I love that question.
Why does it not bounce high as it did the first time?
How come the ball never really bounces back to my hand? Very good question. Somebody else.
Is the ball showing a push or a pull?
Is the ball showing a push or a pull? Very good question. I'll take it. Notice I don't ever answer any questions.
Why does the ball bounce at all?
Why does the ball bounce at all? How come it doesn't hit the ground and stop? I don't have to. The cool thing is I don't have to answer the questions. The purpose of this lesson is to get kids thinking about how do we ask questions. And whether that's a good scientific question or not. And then I pick some of them and we answer them, right? I would have picked the one you asked. Why does the ball not bounce back to my hand? And I would say, hey guys, when the ball is up at the top, it has what kind? And then when I let it go, it has kinetic. But why does it not bounce back to my hand? Something happens at the very moment that the ball hits the ground. Something that we can notice. What do you think it is?
Energy transfer.
Yeah, but what kind? Somebody said energy transformation. What kind? If I had a ball in my hand, especially a golf ball is good for this, the very moment that the ball hits the ground, something happens that we can notice. Sound. The ball hitting the ground makes a sound. But do you remember yesterday we said that sound is a kind of energy? Where did the sound for the ball come from? So the potential energy from the ball when it hits the ground, some of that energy is turned into sound. The ball is losing energy every time it hits, and that's why it never makes it back to my hand. So energy transformations even helps us understand why go home tonight and bounce every ball at your house. Your little brother's soccer ball, your husband's golf ball, the tennis ball. There's not a ball on earth that bounces back to your hand no matter how hard you blow it up. And then I would call the kid up and say, hey, come here. Put your hand on the ground. And I'm going to bounce the ball on your hand. The moment the ball hits your hand, something else happens you can notice. What does the kid say? When the ball hits my hand, it stings a little bit. Why does it sting? The moment the ball hits the ground, it also produces some heat. The bouncing ball loses energy in the form of heat and sound, and the energy lost explains why the ball never makes it back to my hand. But it started with me having kids ask scientific questions. And it's okay that I never answered all of them. Why the ball bounces at all is because the ball has some elasticity. But that's not a part of today's lesson, so I wouldn't even answer that. I know it's not that I don't know the answer, that's just not a part of today's lesson. You know what I mean? I'll tell that kid, hey, go home and Google it. Come back and tell me tomorrow.
Practice obtaining information.
Huh?
Practice obtaining information.
Yes. The first time you ask the kids to go home and write their own experiment, it's going to be uncomfortable. said, Bethel, why can't you just tell us? No. The purpose of this is to teach you how to design an experiment. But if my class is truly rigorous, I'm comfortable and you're comfortable with the uncomfortable moments. I'm uncomfortable when this is hard. I'm not uncomfortable, I'm sorry. I'm okay when this is hard. And it's really not hard, it's just different. I'm asking you to do something different than what you've ever been asked to do. When I teach AP Physics, kids complain, they whine and complain. Because everything's been easy until they get to AP Physics and then they struggle. And I spend the next 6 months trying to show them that AP Physics is not hard. The concepts in AP Physics are really easy. What makes AP Physics difficult is that it is different from every other subject you've ever taken. What makes it different? In math, the teacher teaches you one kind of question, and they give you a sheet full of questions like this. Right? The way to simplify a radical is to divide the denominator, then divide the numerator until you can't divide it anymore, and then the fraction simplified. And I give you a whole sheet full of those. Well, the trouble with AP Physics is that there are no two questions alike, so it's impossible to do that. Right after I teach a kid that F equals M times A, they expect me to give them a sheet full of F equals M times A. And I tell them, well, that only worked for that question. The next question, you've got to use something else, and it's about developing